Okay, today we are gonna start working on solved examples for the assessment and design for. Okay, I'm sorry. Today we are gonna solve some examples regarding the highway capacity analysis cases. So we're gonna start work on problem set number today we are going to work on solving some problems. We're going to work on solving problem set number 1, part 3, capacity analysis and level of service. We solved problem 1 last lecture. Today we are going to work on problem 2 and 3, and we might add a few other more problems. So let's take this problem, grab it. This is the problem that we are going to solve today. It's a new highway segment is going for design. The relevant data are given below. You are required to design this segment at a level of service, target level of service C for the given right of way. Okay. Given the following facts, the average annual daily traffic volume is 54,000 vehicles per day. The directional split percentage is 55%. That's the D. The proportion of traffic occurring during peak hour is 12%. That's the K factor. So these are the main elements that we need to, for the design. So here, what else we know here? Okay. The expected truck percentage is 5%. The right of way is 30 meters. The expected peak hour factor is 0.9. The design speed was 90 kilometers per hour. That means the basic free flow speed is 90 kilometers per hour. The segment length, 800 meters, and the grade is 4%. What's required? Basically, the number of lanes, the lane width, the shoulders, the median. I'm going to just make a slight modification and just modify this to make it 26 meters. Okay. Okay. I'm sorry. So let's start. What we have here is basically a right of way. That means you have here 26 meters to build this road. So let's start first with preparing for the design. Let's calculate or estimate the directional design hourly volume. So the HV equals the average annual daily traffic volume multiplied by K multiplied by D. So that would equal to 54,000 multiplied by the K. In our case, it was here. That's the K, 0.12 multiplied by D, which is here. That's the directional split. So we have here 0.55. This would equal to 54,000 multiply 0.12, 0.55. So here it's 3,564. And this is vehicle per hour. So that's the directional design hourly volume. So how can we start? We start first by assuming the ideal condition. Let's see if we have a shoulder, okay, and lanes, so we're going to assume that we have 1.8 meter shoulder, then the lanes 3.6 meters, okay, then we have a median, then another, then a shoulder. So we have here, say, two. Let's assume that n equal 4. So if n equal 4, so we have here 3.6 and 3.6, and here we have median 3.6 also, and we have another two lanes 3.6, 3.6, and we have a shoulder 1.8. This would equal to 1.8 multiplied, or we can say 3.6 multiply 6. So the total width here would be 21.6 meters. So for n equal 4, let's calculate the VP. VP will equal the directional design hourly volume divided by the peak hour, multiply, in this case, the number of lanes in one direction will be 2, and multiply the factor for heavy vehicle, multiply the factor for population. So let's calculate here the factor for the heavy vehicle. So this factor equal 1 over 1 plus percentage trucks multiply E T minus 1 plus percentage RV multiply equivalent for RV minus 1. So in our case, we have here a segment length and the grade. You know, we didn't have the regular, either the terrain, mountainous, level, or so on. So let's go to the tables and see how can we solve this issue. So if we look at the highway tables or the highway capacity manual tables, here what we got was basically a segment of the road and the grade of that road. So we go to these tables. And these tables, this is for passenger car equivalents for trucks and buses on uniform upgrades. So we are going upgrade, so this is going to be our table that we look for. And here it say the percentage of trucks on buses. Let me just grab a copy of this, take a snapshot of this table. So we can work with it easily. So this is our table here. Let's look carefully at it and try to, find the equivalent truck here. So what we have here, the percentage of trucks and buses, it was 5%. So we are working here. Let me just change. So we are working in this, area. And this is the column of interest for us, because we are working on the 5%. We have 5% trucks. And the grade that we have, it was 4%. So we are here. Okay. So the equivalent truck, the length of the segment, it was 800 meters. The segment length, 800 meters, the grade is 4% upgrade. So we are going to be somewhere here. Okay. And that's 3 to 4, greater than 3 and up to 4. This is greater than 4 and up to 5. So we are at 4. So we can say we are capturing these values. So what's the deal? We just simply take the average. So we will have E truck equal 2 plus 2 plus 2.5 plus 3. This is 2 divided by 4. So the equivalent truck will equal to, I think, 2.5 plus 3 plus 4 divided by 4. So it's 2. I'm sorry, 2.375. So we go and substitute here. So the factor for the heavy vehicles equal 1 over 1 plus percentage trucks 0.05 multiplied by 2.375 minus 1. And there is no RVs in this problem. So this will equal to 1 divided by 1 plus 0.05 multiply 1.375. So this will be 0.9356. Okay. So basically, the VB will equal to 3564 divided by peak hour factor. The peak hour factor was 0.9. 0.9 multiply 2 multiply 0.9356. So VP equals 2,116 passenger car per hour per kilometers. Okay, so the free flow speed equals basic free flow speed minus adjustment factor for lane width minus adjustment factor for lateral clearance minus adjustment factor for median minus adjustment factor for access points. So since most, our design, everything is, typical to the standards, we have a median. So all of these factors are 0 except the access point, and we have nothing related to access points. So we are going to assume there is no access points. So the basic free flow speed here is 90 minus 0 minus 0 minus 0 minus 0. So the free flow speed is 90. Okay, let's check now to see. First of all, the VB is 2,116 passenger car per hour per kilometer. That's a very high volume. So if we look at the tables or the graph here, we are here. So without without going any further, okay, we are far from C. That's the C, and that's where the volume is. So what does this mean? This means that this design, okay, is much higher than level of service C. So we need to modify our design, and let's try a number of lanes equals 6 lanes. Okay, so in this case, our new design will be this way: shoulder 1.8 and a median, then another 3 lanes and a shoulder. So let's see, this is 1.8 shoulder, this is 3.6 median and 1.8 shoulder. And here we have 3 multiply 3.6 lanes and 3 multiply 3.6. Let's check to see if this configuration will be within the right of way or not. So we have 1.8, no, it's 3.6 multiply 6, 7, 8. Okay, so this leads us to 28.8 meters, greater than the current right of way. So what does this mean? We need to change our dimensions and bring it down to 26 meters, which is the available right of way. So in this case, okay, first of all, we try reducing the size of the median and the shoulders. Okay, the last item to reduce from is basically the lane width. So we will reduce the shoulders to be instead of 1.8 to let's say 1 meter. Okay, so this way now we are 27. Okay, so this is instead of 28, it became now 27.8. And we need to remove 1.8 again. So let's take another, say 1.8 meters from here and reducing this to 1.8 only. So this way we are at 26 meters. Okay, so now the shoulders, okay, we still have a shoulder, but it's 1 meter, and we have a median, it's 1.8, okay, and but the lane width, we kept it at 3.6.
دكتور
Yes.
في قيمة مينيموم للميديان؟
That's a good point. You can have the median, down to 1 meter. Okay, and sometimes in multi-lane highway, you can just remove it. Okay, it's not a freeway.
تمام.
Okay, so here the free flow speed will change. So the free flow speed will equal to 90 minus. There is an adjustment factor for the lateral clearance. So the lateral clearance, let's assume that we have maybe posts in the middle here. So the obstacle from here, it will be we have 1.8 meters. So we have here 0.9 and we have here 1 meter. So the lateral clearance, total lateral clearance, okay, I'm sorry. The total lateral clearance equal 1 plus 0.9, so it's 1.9. So the lane width reduction factor is 0, but for the lateral clearance, there is a reduction. So we'll go to the total lateral clearance. Here we have 1.8. There is a reduction of 2.1 kilometers per hour. You see this one here. Okay. So this is 2.1. And the median, there is median, so there is no reduction. The access point is still, we don't have access points. So the free flow speed in this case will be 87.9 kilometers per hour. Let's check and see our new VP. VP in our in the new case will be the directional design hourly volume, which was 3,564 divided by peak hour factor 0.9 multiply 3 multiply 0.9356 equal. So this is 3,564 divided by 3 divided by 0.9 divided by 0.9356. So now we have 1,410 passenger car per hour per lane. And the density in this case will be the VP divided by the free flow speed. So we have 1410 divided by 87.9. So this will be 16.05 passenger car per lane per kilometers, which is just a C. Okay, it's right at the boundary. You see, that's the C, and it's slightly, above the limit. Yani the C. Okay, we can consider this is C, but this is at the maximum. Okay, so in this case, the case that we solved now, we showed how to design from scratch. So how to conduct a new construction. We started with assuming a certain number of lanes, then we checked, then we went to another number of lanes, we increased the number of lanes and adjusted the whole situation accordingly. Any questions? Okay, let's go back again and we let's take this problem. Okay. The problem that we have here, it says that there is a highway segment is going under planning review, given the following facts. The lane width is 3.4 meters, number of lanes and 2 in each direction. Total lateral clearance is 3.0 meters. Median, no median. Okay. The 85th percentile speed was found to be 100 kilometers per hour. That's the basic free flow speed. The peak hour factor is 0.83. The terrain type rolling. Okay. You are asked to determine the maximum peak hour volume that the segment can serve at a level of service C. Make suggestions on how to increase the total capacity while maintaining the level of service at C without major investments. Okay. So let's look here at terrain rolling. I think there's something missing in this problem, which I think it's basically the percentage of heavy vehicles. Percentage HV equal 14%. Okay. So first of all, what is determined here basically was determined the maximum peak hour volume. So let's calculate first of all the at level of service C. Let's calculate the free flow speed. Free flow speed equals the basic free flow speed minus factor for lane width minus factor for lateral clearance minus factor for median minus factor for access points. So here the basic free flow speed is 100 and the lane width is 3.4. So there is a reduction factor for the lane width. So for 3.4, okay, here 3.4, there is a 2.1 reduction kilometers per hour. So there is 2.1. The lateral clearance is 3. It's not 3.6. So there is also a reduction factor for the lateral clearance. 3, there is 0.6. And the median, there is no median. So there is a reduction factor for the median. For no median, the reduction factor is 2.6. Undivided highway. So we have here 2.6. And there's nothing about the access points. So we'll say it's 0. So if we substitute here, then we have 100 minus 2.1 minus 0.6 minus 2.6. So we have 94.7 kilometers per hour. So that's the free flow speed. Now, the problem they are asking for is the determine the maximum peak hour volume, okay, that the segment can serve at level of service C. So let's look at the service volume. Basically, here they are looking for the service volume at LOS equal C. So how can we calculate this? Let's look at the density of C at C equal 16 passenger car per kilometer per lane. Okay, so here our speed is how much? Is 97 here. So if we continue, we can get the maximum volume bear at level of service C. So let's just grab this figure and try to work with it. Okay. As we can see, the speed, the free flow speed, we have 94.7. So it's somewhere here. So let's take a ruler. So here, that's almost in this area. And let's plot a line. So that's the at 94.7. Then let's see where it will hit the flow rate. So if we take projection from here, okay. So that's basically the VB, sorry, that's VB maximum at level of service equal C. So we can say it's almost, this is 1400. It's almost, we can calculate it even. So we can say that the VB maximum equal, what's the speed? 94.7 multiplied by 16. So that will be 1500 passenger car per hour per lane. So that means the maximum volume, the VB max at level of service equal C will equal to the maximum volume at LOS equal C divided by the peak hour factor, the a number of lanes, the factor for heavy vehicles, the FB. So this is what we are looking for. Okay. So in this case, that's the maximum volume at C equal basically the product of VB max multiply peak hour factor multiply N multiply FHV multiply FP. Okay, let's here calculate the FHV. We have the percentage of vehicle 14. So this is 1 divided by 1 plus 0.14 multiply. And it's rolling. So the rolling means we have an equivalent. The equivalent to the truck will be 2.5. Multiply 2.5 minus 1. So the HV equals so it's 0.8264. So let's substitute here and see what we will get. So the VB max will be 1500.15. That's the one that we got here. Here. Multiply the peak hour factor, which was, I think, it was 0.83. Multiply number of lanes, the number of lanes, 2 in each direction. So here we have 2, multiply 0.8264, multiply 1. So this will result in multiply 2, multiply 0.83, multiply 1515. So it's 2078 vehicle per hour. So that's the maximum volume. This is the maximum volume at level of service equal C. That's the first requirement that they were asking for here. Okay, now let's say make suggestions on how to increase the total capacity while maintaining the level of service at C without major investment. Okay, what does this mean? Without adding new right of way, without making a new construction, how can we improve the capacity of this highway? So this is part A. Let's go on part B. What are the strategies that we have that we can do to improve the maximum volume? Okay, first of all, remember that we had here total lateral clearance. Okay, it was 3, and there is 1 lane here, 1 lane, and there was no median. So we had a total lateral clearance, total lateral clearance equal 3.0 meters. Remember, in case of no median, okay, the total lateral clearance equal 1.8 plus the right hand lateral clearance. That means the right hand lateral clearance, or the shoulder in this case, is just 1.2 meters. Okay, so what can we do? And here we have the lanes. We have 4 lanes, 2 in each direction, and we have 3.4 meter lane width. So what can we do? We can just remove from the shoulder and make it 0.8 meters and increase the lane width to be 3.6. That's the first suggestion. Okay, so if we do that, the free flow speed will equal to 100 minus, in this case, there is no adjustment factor for the lane width because now it's 3.6 lane. but the lateral clearance here, in this case, the lateral clearance will be reduced to be total lateral clearance equal, we're going to subtract from here 0.4. So now it's 2.6 meters. So 2.6, let's look in the table and see for a total lateral clearance. Here it's 2.4. Let's take the 2.4, 1.6, 1.5, I'm sorry. So here's going to be minus 1.5 minus 2.6 minus 0 equal. So this will be 100 minus 1.5 minus 2.6 equal 95.9 kilometers per hour. اوكي، يبقى هنا reduce shoulder and increase lane width. So the VB max equal 95.9 multiply 16. So this would equal to 1534 passenger car per hour per lane. So the VB max, or the maximum volume, max volume equal to VB max, the new one, multiply peak hour factor, multiply N, multiply factor for heavy vehicle, multiply FB. So this will equal to 1534 multiply 0.83 multiply 2 multiply 0.8264 multiply 1. So this will be 2104 vehicle per hour. There is no significant improvement using this idea. So there is another idea that we will try, which is basically, in addition to this, we are gonna no heavy vehicles during peak hour. Okay, منع السيارات الثقيلة أثناء ساعة الذروة. Okay, so that means FHV equal 1. So this way, the maximum volume at LOS equal C will equal the VB max multiply the peak hour factor multiply N multiply FHV multiply FB equals 1534 multiply. Actually, we are going to eliminate and go back to the original configuration. 15. We're not going to change the shoulders. We're going to keep everything as it is. but we are going to just prevent trucks from driving through during the peak hour. Multiply 0.83 multiply 2 multiply 1 multiply 1. So in this case, we will have 15 multiply 0.83 multiply 2. Okay, so now we have 2,515 vehicles per hour. Okay, so this choice is much better and yielded better results, as we can see. Okay, شباب. Any questions so far? Okay, we're going to take a break and we will be back, inshallah, after 10 minutes.
دكتور.
Okay, guys, we are back and we are gonna, we have this new problem that we are gonna be solving. It's basically a case that you might face as a construction engineer. The problem reads as following. It's a new bridge passing over a multi-lane highway is being considered for construction. The bridge consists of a slab, okay, simply supported over two abutments, as shown in the attached figure. You are required to do the following. A. Assess the current level of service. B. Develop an optimal construction plan for the bridge abutments, okay, shown in the figure below, such that the maximum drop in the current level of service shall not exceed 2 levels at most. For the bridge slab, you have the following choices available. Cast in place, pre-stressed concrete slab, or precast pre-stressed concrete slab, or composite steel girder reinforced concrete slab. From a traffic engineering perspective, which choice would be optimal and why? Okay, and these are the facts. The peak hour factor is 0.9. The percentage of heavy vehicles is 12%. The volume is 1,752 vehicles per hour. The terrain type is level. The access points, 0 access points per kilometers. The 85th percentile observed speed is 100 kilometers per hour. Note for safety considerations, the basic free flow speed during construction zone, within the construction zone, will be limited to 65 kilometers per hour. Okay, so that's basically the configuration that we have. That's the site. Okay, and these are, these are the we have 1.8 meters shoulder, we have 3.6, we have 2 lanes in each direction, and there is a median. Okay, and these are the abutments that we need to build. And this area, this marks the construction zone, the boundaries for construction. Okay, clear? And this, I think it's 1 meter. Okay, and this will be 3.2 meters. So that means after construction, the shoulder available will be only 1 meter. Okay, so now we want to determine how we are going to construct this. Shall we construct it, the 2 abutments at the same time, or 1 abutment at a time? Because that makes a difference. Okay, for you as a construction engineer, if you can build both abutments at the same time, you are going to save a lot of money. and the project duration will be cut in half. Not cut in half exactly, but will be reduced significantly. But if you have to do this A, then you do B, then your project duration will increase significantly. Okay, and the cost will increase also. So in order to solve this problem, let's work on it step by step. So step one, it say assess the current situation. See what is the current level of service. Okay, so the current level of service, assess the current level of service. So these are the facts here. So current LOS. So first of all, we have peak hour factor, we have volume, we have, let's calculate the free flow speed equals the basic free flow speed minus factor for lane width minus factor for lateral clearance minus factor for median minus factor for access points. So this will be the basic free flow speed is 100 kilometers minus 0 minus 0 minus 0 minus 0, because we can see here that's the cross section, that's a profile. Okay, there's a barrier between the two, where there's a median and there's some barrier, so we have 1.8 1.8, everything is perfect. So the free flow speed in our case will equal to 100 kilometers per hour. We need to calculate VP. VP will equal the volume divided by peak hour factor multiplied by N multiplied with FHV multiplied with FP. So the peak hour factor, we know it. Let's calculate the FHV. FHV, we have percentage of heavy vehicles in our case is 12%. So here we have 1 divided by 1 plus 0.12 multiply. It's a level terrain, so it's 1.5 minus 1. So this will equal to 1 divided by 1 plus 0.12 multiply 0.5 to the, so it's 0.9434. So that means the VB equals 1752 divided by the peak hour factor is 0.92. Here's the peak hour factor. 0.92 multiply 2 multiply 0.9434 multiply 1. So this will result in the following. We have 1752 divided by 0.92 divided by 2 divided by 0.9434. So this is 1009 passenger car per hour per kilometer. No, not per kilometer. This is units for different thing. Per hour per lane. So the density will equal to 1909 divided by, divided by the free flow speed, which is 100. So we have a density which is 10.2 one passenger car per kilometer per lane. That means the level of service currently equal B. So that's the current density is 10 and the limit for B is 11. Okay, so our current level of service is B. So the problem say that we can accept during construction the level of service to drop, but at maximum it can drop to 2 levels. Okay, so it can go down to D. So what we are going to do here, we are going to try, okay, to build the bridge, okay, and building the 2 apartments at the same time. So we are going to try to solve the problem this way. So let's try here B, single phase construction. Okay, so we're going to build both apartments at the same time and see. So if we are going to build both apartments at the same time, that means all what we left with is just this segment. So that means we will have, currently we have here, let me just bring this. Currently we have 1.8. We have 1.8. Let me just change the color. We have 1.8 shoulder. Then we have 2 lanes. Then we have a median. Then we have another 2 lanes. Then we have a shoulder. So this one 1.8, 3.6, 3.6 meters, and the median is 3.6 meters also, and we have 3.6 meter lane, 3.6 meter lane, and here's 1.8 meters. So after during construction, okay, this barrier, okay, will be 3.2 from the beginning of the shoulder. So that means 3.2 meters, and here 3.2 meters. Let's calculate this total width. This total width is basically 3.6 meters multiply 4 plus 1.8 meters multiply 4 equal 3.6 multiply 6. So this is 21.6 meters. If we subtract 3.2 and 3.2 minus 3.2 multiply 2, so the remaining is 15.2 meters. Let's see if we can divide this part into 4 lanes and some shoulders. Okay, so if we divide this by 4, 15.2 divided by 4. What width do we get? Divided by 4, we get 3.8. Okay, so if we take here a shoulder and another shoulder, okay, and this shoulder would be, say, point 6 meters, 60 centimeters, and here 0.6 meters. Then we are going to divide the rest into 4 lanes and see. So this would be 14 divided by 4. So that means we are going to have 4 multiply 3.5 meters. So we are going to have 4 lanes with a lane width 3.5. But we are going to eliminate the median, and we are going to reduce the shoulder significantly, as you can see. So we need to adjust the free flow speed. So the free flow speed during construction, remember, it said that during construction, the free flow speed, the basic free flow speed will be 65. So there is a 65 minus. There is an adjustment factor for lane width. So if we go here and see for a lane width, lane width 3.5 here. Here, the 3.5, we have a reduction of 1 kilometers per hour. So we have minus 1 minus, we have another adjustment factor, which is for the lateral clearance. So in the new case, the total lateral clearance equal 1.8 because there is no median plus 0.6. So it's basically 2.4 meters. For 2.4 meters, the reduction is 1.5. So we have here minus 1.5. And there is no median, so the reduction for no medians is 2.6. 2.6 minus 0 equal. So this will end up in 65 minus 1 minus 1.5 minus 2.6. So this is 59.9 kilometers per hour. Okay. So we have calculated before the VP, okay, the volume, the equivalent lane volume. So the new density that's during construction will be VP divided by the free flow speed, the new one. Let's see now. It's 1009 divided by 59.9, which would be 16.84 passenger car per lane per kilometer. That's good. So that's the density. Let's check to see what level of service this density corresponds to. Okay, as we can see, the C at level of service C, it's 16. So we have 16 something. So we are almost in a D zone, but even on a D plus, you know, almost near to the C. So here, the level of service during construction equal D, which is acceptable because we moved from B to D. So we dropped two level drops. Okay, and that's exactly, so this way we answered part B, so we can have a single phase construction. We don't need to make the construction in two phases. Okay, let's continue and answer the last part. For the bridge slab, okay, you have the following choices: cast in place pre-stressed concrete slab, okay, precast pre-stressed concrete slab, composite steel girder reinforced concrete slab. I assume you know the differences between these three choices. شباب. شباب.
ايوه يا عم دكتور موجودين.
ماشي, okay, I'm asking you. Okay. You know the difference between cast in place pre-stressed concrete slab or precast pre-stressed concrete slab, composite steel girder reinforced concrete slab?
Yes, doctor.
Okay. So in this case, which choice would you take? And why?
I think doctor precast.
Precast. Good.
Yes.
Why? Now that's the most important. Why you want to go with the precast?
I think we can reduce the duration of the construction with the precast concrete.
Okay. That's one point. Okay, that's from a project management perspective. But from a traffic perspective,
Can finish the road quickly, so no more traffics in the daily life.
okay. First of
People.
all, this choice is ruled out because basically you need to have form work, okay, that will be complicated, okay, to have it on the road, okay. But the precast is much easier, okay, but by putting the slabs on top of the apartments and continue, you know, and maybe this one also, composite steel girder, okay, but the first one is ruled out. Okay, any questions? Okay, by this example we are concluding our first module, and next week inshallah we are going to start on the second module, which is basically the geometric design of highways. Okay, I will stop here and see you inshallah next week.
يعطيك العافيه دكتور. شكرا.
But before we, okay, hold a second, let me just shut down the printing.